general relativity step by step. Last time I introduced the Penrose transformation and showed you how it worked for flat space, and I had a few nice examples here. And the distributions, the transformations look a little bit like this for flat space. It's entirely possible to have the same transformation, but to use it to try and understand a black hole. And I've done that here with this picture here. Hold on a minute. There we go. Just make that a bit bigger. Here we go. So this is a Penrose transformation of space with a black hole in it, and we can see a whole bunch of nice features. What it's done, it's changed the hyperbolic nature of the singularity to a nice straight line. This is using the Cauchy distribution. What else have we got here? We've got a whole bunch of other things that we can talk about on this diagram. We've got the horizon and the anti-horizon here. We've got the event horizon formed here. But we can see that we've represented the whole of space-time outside the black hole in this diamond-shaped region here. We can see that the radius goes to infinity here, although I've not been able to draw very many of those. And we can see that the radius approaches 1 as we go along this direction here. What else have I got here? I've put ingoing light rays. We can see that the ingoing light rays are nice 45-degree lines, and outgoing light rays are drawn in blue here. We can also see, what else can we see? We can also see the behavior of the, it's jumping about. We can also see the behavior of space-time inside the black hole here, and we can see that here, of course, the radial coordinate is behaving more like a time coordinate, r is behaving like a time coordinate, and t is behaving like a spatial coordinate. So when you're in here, you're sort of you're not drawn towards it as such. It's just that as your local time increases, you find yourself hitting the singularity with inevitability. You cannot avoid it. I quite like this diagram. It shows the whole universe as being only twice the area of the region inside the black hole, which is this triangular region here. But that's okay. We wanted to transform the whole of space-time into a finite area, and so the area doesn't really matter. The area isn't an important consideration here. So that's just a beautiful diagram to conjure with. I want to make the observation that I've used the Cauchy distribution here, but I could use other distributions, and I'll show you what happens if you use some other distributions for the Penrose transform. You get diagrams like this. Qualitatively it's the same, but the singularity, the r equals 0 line here, is a distorted version. It just so turns out that the Cauchy distribution's got nice mathematical properties to make the singularity a nice horizontal line. And also the space outside the black hole doesn't look as nice as it does in the case of the Cauchy distribution. And while I'm doing it, I also did the Gaussian transformation, which looks even worse. You see, it's not a pleasing diagram. So when you do it, you normally use the Cauchy transformation and leave it at that, which is this one here, and it's a beautiful demonstration of transformation of coordinates to lead to physical insight. A beautiful diagram. I'm going to stop there. Stop.